All right, everyone. Shall we start the lesson? Um, Let me know if I am not in any way audible or if you feel that there is a lag in the connection also. Just let me know in the chat. So we're going to start this new lecture today, and we'll be finishing this lecture off on constraint optimization. Um, so before I start, now I've been, hold on. So I've been marking your mid-sem papers. It's not yet done. Um, what I wanted to do through the mid-semester exam is to identify. Now, I gave you a model paper and to see whether you identified the similar type of questions that were given in the model paper in the mid-sem exam. And I sometimes see that some students find it still difficult to understand that mapping because I'm not checking your math knowledge there because most of the questions I would say were very similar to the questions I gave in the model paper. And if one practice those model paper questions, this is quite straightforward, I would say. So I didn't test your math knowledge. I tested whether you were able to map similar type of problems and give a solution to it. So that was the objective. Once I see the final results, I can decide how to set the final exam paper. In the final exam paper, of course, I will give for you to choose questions from. I haven't decided whether to give 6 or 7 questions and then answer four. Definitely, you'll have to answer 4 questions, but out of how many? Whether it's 5, 6, or 7, I haven't decided yet. I'll let you know in advance. Um, right. So, constraint optimization. Now, why do we have this particular lecture? Because all this time, we were talking about finding maximums and minimums or saddle points in a given function which had no limits. So the function was not limited by something. Whereas in the real world, when you consider economics, obviously there are limitations or constraints applied to some function that you're analyzing. For example, if you take a consumer problem, a consumer would want to maximize his or her utility, but they're obviously constrained by things like their budget, the income that they get. And if you take a problem for the firm, a firm wants to obviously maximize their profit, but they're obviously constrained by so many things. Maybe it could be their input costs like labor cost or capital cost, likewise. So we want to understand, given a set of constraints, how do we maximize or minimize a given objective function? So I know I had a question on this in the paper. That was mainly because like I said, I wasn't testing your math skills. I was testing whether you were able to map the similar type of problems in the model paper. So in the model paper, I had a question on constraint optimization. And some of you have got it correct in the midsem paper as well. Right. So on constraint optimization, we are going to use this method called this Lagrangian multiplier. That's what we're going to use. But before we get to constraint optimization, the first section here, what we're talking about is unconstrained versus constrained optimization. So earlier, before this lecture, we were talking about unconstrained optimization. So you have a particular function, and then let's say f of x, and then what would you f of, let's take several variables, x1, x2, up to, let's say, n variables. Then what I try to do, by partially differentiating the function with respect to each of these variables and equating it to 0, you try to figure out, and these were called first order conditions. These are called first order conditions. By partially differentiating and equating it to 0, you try and figure out x1, x2 up to xn, what their values are, and then You use this thing called the Hessian matrix, which we talked about, Hessian matrix. And using in the Hessian matrix, um, if it's a positive definite or a negative definite, we were able to tell whether it was a local minimum or a local maximum. That's what we did on the unconstrained optimization. We have this particular function which had no constraints at all. We partially differentiated it with respect to its independent variables, in this case x1, x2 up to xn. We equated it to 0. We figured out what the values are for x1, x2, and up to xn. And then we figured out whether these values that we found out are giving us a maximum value for simple f or a minimum value for simple f. And for that, to figure out whether it's giving a maximum or minimum, we use this Hessian matrix. But constraint optimization is a little different. Why? Because your choice variables can't vary freely. That's what I'm saying here. You can't vary them freely because it has to satisfy some conditions. And that's what is key here. So, for example, I've taken, let's take away these lines. So, for example, I'm considering a consumer, as I said before, would want to maximize his or her utility, but they obviously have something like a budget constraint. So, capital M here is income, and they would have a budget constraint. So, the feasible set of points which would maximize his or her utility would be restricted to the given constraint function, which is this, right? The budget constraint. So, how would you try to solve such a problem? If you're told your utility u of your x1, x2, you're trying to maximize this, but you're trying to maximize your utility, but it is subject to a constraint which is in the form of gx1, x2, which is you have two goods. So P1 is your price of good X1. P2 is your price of good X2. But you have a particular income you're getting. So this aspect, this is your expenditure part, and this is your income. Given your income, by how much can you spend such that you maximize your utility? How do you solve a problem a problem like this? That's the key question we're going to ask and answer through this particular lesson. And the key method that we are going to use to solve a problem like this is called the method of Lagrange multipliers. So in the method of Lagrange multipliers, we are specifically looking at this thing called equality constraints. So even in this case, our constraint, you see there's an equal sign, right? Um, there can there are also problems where this particular constraint, now this here is a equal. You can also have a problem where your constraint, this is your constraint, this is your constraint, um, can also be an inequality like this. Let's say, hold on, me rewrite it. P1 x1 plus P2 x2 is less than or equal to m. So you can have a problem where you have an equality sign. Whereas at the moment, to keep things simple, we are looking at problems of the form like this, where your constraint is an equal, right? So your on your left-hand side, you have your expenditure. On your right-hand side, you have your income. So basically, you're spending all that you get here. Whereas in your inequality sign, you're not spending all your income, all your income. So that's the difference. And when you have an inequality constraint, the method you use slightly changes. So we'll look at that later on. Right. So let's have a look at this Lagrangian method of Lagrangian multipliers. So if you consider a general problem like this, where you're trying to maximize a function f of xy through your independent variables x and y, but you're subject to st is subject to a constraint g of xy equals to c, right? C is some constant value. So how do we go about this particular method? That's what I have given here in step-by-step format. First, you form the so-called Lagrangian function. So what does the Lagrangian function consist of? I would write it in this particular L format. It has, in this case, three variables, x, y, which we initially had, and a new variable introduced called the Lagrangian multiplier. This is called lambda. This is called lambda, the Greek term lambda, and it's officially called the Lagrangian multiplier. So the Lagrangian equation is L of x by lambda equals to the objective function. So this here is your objective function. This is the objective function. Your objective function plus the Lagrangian multiplier times, so you're multiplying it by c minus g of xy. So this here, this part over here is coming from your constraint, c minus g of xy. Now, some people get a little confused and they make mistakes. Where do they make mistakes? In this particular um, sign over here. Sometimes you use plus, sometimes you use minus, and people ask, oh, when do you use plus and when do you use minus? So stick to one thing and be consistent. Now, in this case, what I have used is the plus sign. You would use the uh, minus sign in the case of, if you write this down, f of xy minus lambda times, then you would simply change this internal function rather than saying c minus g of xy, which we had over here, you would say g of xy minus c. So you see, then your sign changes, right? So what I would suggest is you stick to one. When you're looking at YouTube videos, folks might use different signs, but understand what's going on. The changes in this particular part over here. So um, I think we'll try to use the plus sign, might use the minus sign. But anyway, what you need to keep in mind is the Lagrangian function is given in this form. So that's the first thing you need to do, right? So you form the Lagrangian. And then once you form the Lagrangian, let me rewrite it again so that it's easier. So your first step number one, is to write down the Lagrangian xy of lambda, objective function, which is of two variables in this case, f of xy, plus your Lagrangian multiplier multiplied by um, c minus g of xy, which is your constraint. That's step number one. Step number two is to form the first order conditions. That's what I mentioned here. You form the first order conditions. So now, how do you form the first order conditions? You have three independent variables, three unknown variables. So you're going to partially differentiate your Lagrangian function with respect to x. Lagrangian function, you're again going to partially differentiate with respect to y, and partially differentiate your Lagrangian function with respect to lambda. And from this, you get three equations. So let's look at the first one. Partially differentiating your Lagrangian function with respect to x, you get, you partially differentiate your objective function. That's what this symbol means. When I say over here, what this means is I'm partially differentiating function f with respect to x, all right? Because it has an x in it, plus I have lambda times 0 minus, because when you're partially differentiating a constant with respect to x, it's 0. Again, I have x where in the function g, so I partially differentiate the function g and I equate this to 0. These are my so-called first order conditions, right? So this is equation number 1. This is equation number 1. Then I move on to partial differentiating the Lagrangian with respect to y. So then I partial differentiate my objective function simple f with respect to y plus lambda times, when I partial differentiate a constant c with respect to y, it's 0, minus I have the g function which also has y, so I partially differentiate it with respect to y and I equate it to 0. And finally, I partially differentiate the Lagrangian function with respect to lambda. Now the objective function does not have the lambda component, so that's 0, plus um, I have c minus g of xy times lambda differentiated with respect to lambda is 1, and then I equate this to 0. So where do I have lambda? The only place I have lambda is only here. So if you remember the differentiating rules, this is a multiplication. So that's what I have used here. So then from this, you see, I have two, three, I have 3 equations and 3 unknowns. What are the 3 unknowns? X, y, and lambda. So what I have to try and figure out is what are these x, y, and lambda. So if I were to rewrite the 3 equations, so rather than writing double by double x, I would write L of x, which gives me f of x, xy, minus lambda times g of x, xy equals to 0. That's first equation. Then I have the second equation, Lagrangian partial differentiated with respect to y, which equals to the objective function partial differentiated with respect to y, minus lambda times g partial differentiated with respect to y equals to 0. That's your second equation. And finally, I have Lagrangian partial differentiated with respect to lambda. There I get the constraint directly and I equate it to 0. That's my third equation. And that's what I have got over here. So the first order conditions gives me these 3 equations. That's step number 2. All right. So what you're seeing here, so I've said here, the first two equations, that's this one and this one, set the gradient of f equals to lambda times the gradient of g. What do I mean by gradient? Gradient here is I'm basically partially differentiating um, uh, the functions f and g. So the symbol for gradient is this sign, this kind of triangular sign upside down. That's the gradient function. So what you're doing is you're partially differentiating your functions f and g with respect to x and y, and you're from the first two equations you see that your gradient of f of xy equals this Lagrangian multiplier times the gradient of g of xy. So when I say gradient, it's basically from 1 you get f of xy equals to lambda times g of xy, and from 2 you get f partially differentiated with respect to y equals lambda times g partially differentiated with respect to y. So rather than putting it like this, you can simply write it also. That's what I've given here as the gradient of the function xy equals the gradient of the function g of xy, where this particular operator, what does it mean? It is simply taking the operators dabba y because you're partially differentiating with respect to x and y, your functions g of xy, right? So what you have done is lambda times, sorry, I have to make it lambda times. Now I'm getting a little mathematical. You don't need to do any of this. I'm just simply trying to explain this. And if you don't get the full picture of it, that's completely fine. So you're partially differentiating xy by x. That's your first equation. And you're partially differentiating your function y with respect to y, lambda times you're partially differentiating your function g with respect to y. That's your second equation, right? So this is what you have got basically over here. So I've simply put it as f of x, xy, f of y, xy. But what you're really doing is something like this. And what this symbol over here does is simplifying, writing all these big equations. You can put like this. So the gradient function, right? So that's step number 2. What did we do in step number 1? We formed the in step number 1 we formed the Lagrangian, which has the objective function component, right? And your constraint function component, and you have this Lagrangian multiplier. So that's 3 components. Then you do the first order conditions and you equate them to 0. So what are the first order conditions? So in this function, your input variables are x, y, and you have introduced lambda. So you have x, y, and lambda, and you equate it to 0. You partially differentiate to a Lagrangian. You partially differentiate this Lagrangian with respect to x, y, and lambda, and you equate it to 0. And then you get these 3 equations over here. And from those 3 equations, you have 3 equations and 3 unknowns. You solve for x, y, and lambda, right? And that's the third step. You solve for x, y, and lambda. And when you find the x, y, and lambda, there's an interpretation for your lambda. So, for example, let's see what I've said here. So it turns out that lambda star, the optimal lambda, equals the marginal increase in the objective if the constraint is relaxed by 1 unit. That's the more generalized answer. So what is this optimal lambda that you found? It's the marginal increase in the objective function if the constraint function is relaxed by 1 unit. So for example, so I also say lambda is the shadow price. For example, if your function, objective function, is utility and your constraint function is the budget constraint, then lambda star tells us how much the maximum utility would rise if the consumer had $1 more. Lambda star tells us how much your maximum utility would rise if the consumer had $1 more. So that's an example uh, of lambda, how you interpret lambda. Right. Let me first take away all these drawings. So what we are talking about over here is the method of Lagrangian multiplier, where we have a constraint optimization problem of the form you have an objective function subject to a budget constraint. Then you use this Lagrangian method, you form the Lagrangian equation, and then you take the partial derivatives and you consider the first order conditions. From those first order conditions, you figure out your independent variables plus the Lagrangian multiplier, which you introduce, lambda. And once you solve uh, for x, y, and lambda, you interpret what lambda is given the particular context. And then obviously you also have to check whether this x, y are giving you the maximum or the minimum for your objective function, which we'll talk about later. So here, step number 5, I've just generalized this. Now earlier I had 2 independent variables. Here we are talking about if we have n independent variables with m independent equality constraints. Remember, we are talking about equality constraints. So earlier, what did we have? Earlier we had only 2 independent variables for your function subject to only one equality constraint. So you had only one equality constraint. Now, in this particular case, we have n, just to generalize, n input variables or independent variables subject to equals to C1, subject to you have m C2, likewise you have m constraints, right? You have 1, 2, up to m constraints. So in that case, how would you form your Lagrangian is what I have given here. So then in that case, your Lagrangian is x1, x2 up to xn. You have n choice variables. Since you have m constraints, you introduce m number of Lagrangian multipliers. For each constraint, you have to introduce a Lagrangian multiplier. So therefore, that is why we write this down as your objective function. It's the same component. Plus, now you have lambda 1 times c1 minus your g1 function. That's 1 plus lambda 2 times c2 minus your g2 function, plus likewise you have m number of constraints, so lambda m cm minus gm, right? So that's what I have, without writing all these plus signs, I have written it down using the summation equation sigma lambda c minus g, where I put in, rather than saying 1, 2, 3, I put in I, right? The notation I, where I goes from 1 to m. And that's what I have written here. So that's the more generalized Lagrangian equation. Okay, now, before we go to solving an example problem, I want us to watch this particular video for you to get an understanding about a visual understanding of what this Lagrangian multiplier method is. Let me know if the audio is not clear.
One of the most powerful applications of calculus is optimization. Indeed, if I'm given some function, how do I know that function is going to have a maximum, and how do I know when it's going to have a minimum? However, what we're going to do in this video is look at a special type of optimization, a special type of trying to find maximums and minimums. It's when I ask you to find the maximum or the minimum, but I give you a constraint, I give you a restriction. For instance, consider this graph. What I have is just the graph of some function, the function xy plus 1. And the graph itself, well, it has a saddle point at the point 0, 0, but it then goes up in one direction forever and goes down in some other direction. However, if I impose a constraint, if I say it has to be on this particular curve, and I'm asking, what is the maximum of this function restricted to that curve? What is the minimum of this function restricted to that curve? The blue curve that I put up here, if I look at it in the domain of my function, is just the equation of a circle. X squared plus y squared is equal to 1. So in the domain, I have a circle, and I'm saying you are restricted to that circle. And then in the graph of the function, you look at, well, what does the function do above that circle? And the question is, what's the maximum of the function on the circle, and what's the minimum of this function on the circle? This video is going to talk about something called Lagrange multipliers. And Lagrange multipliers are going to give us a method to figure out the maximums of functions like these when you're constrained to specific constraints like this circle. For instance, I've highlighted here in the red dots the maximums of the value of the function constrained to live on the curve. And then in the domain, the two red dots say, well, where in the domain am I going to have these maximums? Also looks like I have two minimums as well. To help me understand what's going on here, I put up contours on the graph of my function. Remember that what the contour is you telling me the height is constant. So I'm setting the function value, this xy plus 1, equal to various constants. And then I get these resulting curves. So for instance, if I set it equal to the value of z equal to 2, you get one curve. If I set it z equal to 1.5, you get a different curve, and so on. This gives you a bunch of level curves. And then I can look at what these look like in the domain as well. Well, if I take this sort of bird's eye view and I look straight down, then I get this similar kind of effect. So I've got my blue circle, the restriction, and then the yellow curves are the level curves of the original function. For instance, if I take that z equal to 2, then I have the z equal to 2 looks like two pieces of these curves, and z equal to 1.5 is moving in a little bit, and so forth. Indeed, the way I compute these is that the output of my function is 2, so xy plus 1 is 2, then that means that xy is 1, which means that y is just 1 over x. And so indeed, this curve here is just representing the equation 1 over x in the domain, and then it has the height of 2. Now, of all these different level curves, one of them is special. One of these level curves only just barely touches the restriction. Here, I'll focus just in on this one. This particular level curve has the property that this level curve goes right through what looks to be the maximum of this function. And indeed, if I look at what happens down in the domain, that level curve, it comes along and just barely kisses the constraint. And this restriction that I'm choosing the particular level curve that comes in and just barely touches it, that's going to be my candidate to be a max or a minimum, well, if it just barely touches it, it means something about the equation of tangent lines. In particular, what it means is that the equation of the tangent line to the constraint, the equation that's just a circle, the x squared plus y squared equal to 1, that's got a tangent line. And the level curve also has a tangent line. And if they come along and just meet, those tangent lines are the same thing. So at the two spots where this particular curve comes and just barely touches the constraint curve, then the tangent line is shared by both of these curves. Indeed, if I put all the curves back on here again, you see that this case is pretty special. You'll see that some of the level curves don't intersect at all, in which case they're just not relevant. They can't be part of that constraint. They're not even on the constraint. And then some of the level curves, they come in and they intersected at multiple places, but those values have lower values than the one that just comes and touches at the one spot. If you imagine sort of continuously varying the height as you move your level curves up, well, as you go up and up and up and up, at one point you just finally stop being subject to it. Indeed, if I took that special one, the one that's just come along and just kissed it, if I moved it even a little bit higher, it would no longer intersect the constraint anyway. It would no longer be relevant. So the one particular level curve that just comes and kisses it, that's going to be your candidates for maximums. And indeed, as we can see here, we also have minimums where it just comes and kisses it in the other direction along y equal to minus x, where it just kisses it. That's your candidates to be minimums. Okay. Let's take this geometry and try to study it a bit more algebraically. So I'm going to return back to the simplified picture. And what I want to notice is if they share a tangent line, then their normals are also related. For example, let me look at the constraint, the blue circle here. There is a normal to that curve, and you may recall that the gradient vector always is normal to a level curve. So at these 2 points, the gradient of g is normal to the particular level curve, and indeed it's normal to this particular tangent line. Likewise, if I look at the normals to the level curve of my function, well, I'm also going to get a gradient of f, and my gradient f and gradient g, they're both normal to the same tangent line. So the gradient of f and the gradient g are both normal to the same tangent line. And if the gradient of f and gradient of g are both normal to the same tangent line, what that means is they are scalar multiples of one another, that the gradient of f might be twice or 1/2 of the gradient g, but either way, it's in the same direction. So this picture that I have motivates the Lagrange multiplier method, and it goes a little bit like this. There are two relevant equations here. The first equation is a relationship between these two gradient vectors. It's what we just talked about geometrically, that the gradient of f is just some multiple of the gradient of g. Lambda is just some constant, and it says that these two vectors are just a multiple of the other. And then the other equation is the one we began with. We had the original constraining equation, g equal to 0, so that hasn't gone anywhere, so that's still here. So I'm trying to maximize, and that means I got these two conditions, this business about these gradients being scalar multiples and the original constraint, the g equal to 0. Okay, so let's plug in the formulas and see what we get. So first of all, we started with our function f of x equal to this xy plus 1. That means that my gradient of that is just going to be yx. The gradient is the partial derivative with respect to x in the first component, that's just y, and the partial derivative with respect to y in the second component, that's just x. Then if I look at my constraint equation, the g, I can do the same thing. What is the gradient of this? Well, again, I have to figure out the partial derivative with respect to x, partial derivative with respect to y, and what I'm going to get is 2x and 2y. Both of these gradients are easy to compute. So if I look at the two different equations that I sort of begin with, it turns out that these two equations are really three equations in three unknowns. The unknowns are the x and the y, and this new thing we've come up, this lambda. So there's three unknowns, an x, y, and a lambda. But there's really three equations, because the first equation is a vector equation. Gradient of f is lambda, gradient of g is equating two two-dimensional vectors. So the first components of that is the first component of gradient f is lambda times the first component of gradient g. In other words, just y equals lambda times 2x. Comparing the second coordinates of this, now I'm saying x is lambda times 2y. So the second component of gradient of f is equal to lambda times the second component of gradient of g. And then my third equation is the good old constraint that we've always had, the x squared plus y squared minus 1 is equal to 0. So these are my three equations. Now, depending on your problem, the specifics of the algebra of solving these equations simultaneously, that might change. In this particular case, it's relatively straightforward. What I'm going to do is I'm going to take the second equation, the x equal to lambda 2y. I'm going to plug it into the first, and that's going to give me the equation that y is lambda times 2 times the lambda times 2y. You put all that together, you get y is 4y squared times y. Now, this equation has two possible answers. One solution is just that y is equal to 0. You just have 0 on both sides. If y is non-zero, then you can divide out by the 0. And then if you solve that, you get lambda is equal to plus or minus 1/2. Now, in the first case, if y is equal to 0, then reading off into the first or second line, you get that x is equal to 0. And 0, 0 was not on the original ellipse. The ellipse x squared plus y squared equal to 1. So this is just not actually a solution. This does not satisfy the third equation. So and if I take the lambda equal to plus or minus 1/2 and plug this in, this tells you I have a relationship between y and x. Y is plus or minus x. And now that I know this, if I take the y is plus or minus x and substitute it finally into that third equation, into that constraint, I get x squared. Then I get, minus x all squared is equal to 1. This tells me 2x squared is equal to 1, so x is plus or minus 1 over root 2. So there's really four possibilities here. X is plus or minus 1 over root 2, and y is plus or minus those values, so also plus or minus 1 over the square root of root 2. So there's four different possibilities for the x's and the y's. So I've returned back to the geometry where I've got the graph of my function and where I've got my domain specified. And what I've done is I've taken two of those 4 points, and what you can see is that for two of those 4 points, those do represent the maximums of this function. If you wished, you could plug these numbers into the function, you would get the value 1.5. That is the maximum of this function constrained to this particular equation. Likewise, for the other two, well, they represent if I shift the situation, I now not ask for maximums, but I ask for minimums. They give you a slightly different pair of points, and you get a different level curve. Now it happens to be equal to a height of 0.5. And these 2 points are at the minimums. So notice that just by getting those 4 points, I didn't know which was maximums and which was minimums. The idea of Lagrange multipliers is that this geometric analysis that we did gave a very nice extra equation. The gradient of f was lambda gradient of g. That equation was in addition to the constraint that we already had that g was 0. When I looked at those equations and solved them out, what they gave me were all of my candidates to be maximums or minimums. I didn't know which were maximums and minimums ahead of time, but if you then evaluate your function at the points, in this case the 4 points that we had, you can see that 2 of them were going to be the same value in the maximum and 2 of them were going to be the same value in the minimum. If you have a question about this video, leave it down in the...
Okay, so hopefully that kind of gave you a quick visual understanding. You can always go back and watch watch a similar type of video to get a visual understanding of what we're doing. Remember, we're talking about constraint optimization because in real economic problems, you're trying to maximize or minimize some objective function, but you always have limitations. And remember, this is heavily used. These problems are heavily used actually in problems called DSGE. I think I mentioned this to you. Dynamic. This is an application of these Lagrangian multipliers. Dynamic stochastic general equilibrium models. General equilibrium models. These are models used by macroeconomists, some central bankers as well. So this concept of Lagrangian is used in such models as well. So there are macroeconomic applications for what we are learning. Right. So let's move on to this particular example. So we are told practice problem 2.1, applying the Lagrangian multiplier method. A farmer wants to maximize output from two crops, corn and wheat. Corn is given by X, wheat is given by Y, given a fixed amount of land. So you're told that suppose the production function is given by this, where X and Y are acres planted with corn and wheat. The land available is 16 acres. So the constraint is X plus Y equals to 16. So first we set up the Lagrangian. So we are asked to maximize the two crops X and Y given by the production function f of xy equals 5 times root x plus 4 times root y, subject to the land constraint, which is given by x plus y equals to 16. So the first thing that we have to do is set up the Lagrangian xy lambda. There's only one equality constraint. So we introduce one Lagrangian multiplier equals to, the first component is the objective function plus lambda times the equality constraint, 16 minus x plus y. We set it up. That's step number 1. Step number 2 was to write down the first order conditions. That is, partially differentiate your Lagrangian with respect to x. So here you would get 5 times root x. When you differentiate that, you would get 5 time divided by 2 of root x. 4 times root y is 0. So you don't differentiate it with respect to x. Time plus lambda times minus 1, because you have minus x over here, and you set it equal to 0. So rather than just writing lambda times minus 1, I'll say directly minus lambda equals to 0. That's your first equation. And then you partially differentiate your Lagrangian with respect to y, and then you have 4 times root y, so that would be 4 divided by 2 times root y minus lambda equals to 0. You check in your Lagrangian where you have your y and you partially differentiate. So again, you have y over here. So you partially differentiate it. The third equation would be you partially differentiate your Lagrangian with respect to lambda. So that would be simply uh, your constraint function, and you equate that to 0. Now you have three equations and three unknowns. What are we going to do? So first and foremost, from 1, I get 5 divided by 2 root x equals to lambda. From 2, I get 4 divided by 2 root y equals to lambda. So I'm going to divide 1 by 2. So then I get um, 5 over 4 y over x root equals to 1, because lambda lambda cancels out. And that means um, if I square everything, I get 25 over 16 times y over x equals to 1. So therefore, I get x is equal to 25 over 16 times y. And I go and substitute this. Let's say this is 4. Substitute 4 in 3. So I get 16 minus x is now 25y over 16 minus y equals to 0. Um, so I have 16 equals to 25y over 16 plus y. I take all the y's to one side. Then I make y the subject. So 16 times 16 divided by 41 equals to y. From this, I should get y to be, let's call it y star now. Y star is around 6.24, somewhere there, some value like this. Um, Using this y value in equation 4, I can get x. X is 25 over 16 times y. What is y? 16 times 16 divided by 41. So therefore, I would get x star something like 9.756. Right? So you know your x and your y. So you can use either your first equation or second equation. Now let's compute lambda star. So from your equation 1, um, you get, what was it? 5 over root 2x equals to lambda. 5 over root 2x equals to lambda. So lambda star is 5 over 2 times what is root x? X is, if I write it down, 16. So x is 25 times 16 divided by 41, the square root of this. You should get something like 0.801. So you should get lambda star to be 0.801, right? So this is how you go about computing x, y, and lambda for this given problem. So you had to maximize your function f of xy, which is 5 root x plus 4 root y, subject to a constraint, which was x plus y equals to 16. This was your problem. So step number 1 was to write down the Lagrangian. That's what you did. So this component is your objective function plus your Lagrangian multiplier times, you multiply that by the constraint. Step number 2 was to calculate your first order conditions. So the first order conditions are with respect to your input variables x, y, and your Lagrangian multiplier. You partially differentiate your Lagrangian with respect to those variables, and you get these three, and you equate it to 0, and you get these three equations. So you have three equations and three unknowns. What are the three? You have three equations and three unknowns, right? So x, y, and lambda are your unknowns. So from that, from the three equations, you compute your x, y, and lambda. Right. So that's the solution I have given here. So I've written it down. So you can go through the solution. I just did this here as well for your reference. And then you have to write down the interpretation of lambda. So what do you mean by this 0.801 that you get for lambda? So that's what I've written here. So 0.801 is basically the marginal output from an extra acre of land at the optimum. So if the farmer had one more acre, output would increase by roughly 0.801 tons. So that's what we are saying here. Lambda star is where if the farmer had one more acre, 17 instead of 16 acres, his uh, production would increase by about 0.801 tons. That's what lambda means. Right now, we calculated your x star, y star. Now, how do we know that this x star and y star actually maximizes your function, your original function, your production function, this, right? How do we know that? To prove that only, we are going to look at this thing called second order conditions. Second order conditions. So by using these second order conditions, we can prove that whatever you got for x and y would either maximize or minimize your original objective function. Right. Now, under second order conditions, if we were to look at the unconstrained case, we use the Hessian matrix. I think I've talked about this before. So in the unconstrained case, yes, you have the Hessian matrix. So if you have a function of x and y, if xx is basically partially differentiating a function twice with respect to x, if xy is you partially differentiate your function first with respect to x, then with respect to y. If y comma x is you partially differentiate your function with respect to y first and then with respect to x. So in our economic problems, usually we equate these two. We get these two as equal, but not always. If y is basically your partial differentiating a function twice with respect to y. So then you put it down in matrix format, and then you calculate the determinant. You calculated the determinant of this matrix, and if that determinant is negative, we say we get a local maxima. If the determinant is positive, we get a local minimum. That's what we had in a unconstrained case. Now, in the case of a constrained optimization, which is what we are interested in, we have something called the bordered Hessian. We have something called the bordered Hessian, very similar to the Hessian matrix, but we are introducing certain other things. Now, in this case, we have a constraint function. We wrote down the Lagrangian in this particular format. So the bordered Hessian, if you look at this, is written. So let me write this down. B equals bordered Hessian matrix. Let's write down 0, gx, gy, gx, gy. I'll explain what these terms mean. Lxx, Lxy, Lyx, Lyy. So in the bordered Hessian, the first row and the first column, right? So always this first element, first cell, first row, first column cell is 0. What is gx? Gx is simply partially differentiating your constraint function with respect to x. What is gy? It is simply partially differentiating your constraint function with respect to y. Then what is this L of xx? L of xx is partially differentiating your Lagrangian function twice with respect to x. What is L of xy? L of xy is it's very similar to what we did before with the Hessian matrix. Partially differentiating your Lagrangian function first with respect to x, then with respect to y. And similarly in this case and in this case. So Lyy is partially differentiating your Lagrangian with respect to uh, second order derivative of your Lagrangian with respect to y. So we write down this bordered Hessian matrix, right? So we write down the bordered Hessian matrix 0, partially differentiated constraint function with respect to x, partially differentiated constraint function with respect to y. Same thing over here, copy pasted. And then you have your Lagrangian function partially differentiated with respect to x and y, and finally y and y. So this is your bordered Hessian matrix. From the bordered Hessian matrix, uh, how do we identify the two given values x and y are either maximum or a minimum? So what we do in the case of a local maximum is we look at two conditions. So we are looking at the local maximum case, local maximum. So in the bordered Hessian matrix, we take this part first, this part, which is, we call it, let's call it simple h, because that's kind of like the Hessian matrix, 0, gx, gx, L of xx. And we take the determinant of this matrix, and then we take a bordered Hessian matrix, the full thing over here, and we take the determinant of that, determinant of B. So this is a 3 by 3 matrix, this is a 2 by 2 matrix. We talked about matrices and determinants, and this is an application of matrices. And then we see if the determinant of H is negative and the determinant of B is positive, we say we have a local maximum. And in the case of a local minimum, similarly, we take the Hessian matrix 0, gx, gx, lambda xx, the matrix, and we consider the determinant of this again, determinant of H. We take the bordered Hessian matrix 0, gx, gy, gx, gy, lxx, lxy, lyx, lyy, and we compute the determinant of B. In the local minimum case, what needs to happen is the determinant of H is positive and the determinant of B is negative. Then we say we have a local minimum, and that's what I mentioned over here. So you see that local maximum, the 2 by 2 minor h is negative and the full determinant of b is positive. In the local minimum case, this h is positive, the determinant of h, and the determinant of b, remember these are determinants, we have to calculate determinant of h and determinant of b, is negative. So you see that the sign is varying. How you can remember this is, in the case, how you remember, this is not true, but this is how you can remember. So in the case of a local maximum, your function would look something like this in the 2D space, right? So you have your xy in a 2D space. This would be a maximum. So you see, um, let's take, sorry, x, y. So this here. So this is your maximum point. So what is happening is your sign is changing from a negative tangent to positive tangent to a tangent in a local maximum case. And that is something similar that's happening in the sign changes. Determinant of H is negative, determinant of B is positive. Whereas in the local minimum case, the local minimum case, your function, let's say, would look something like this. It's changing, the tangent line is changing from a minimum, from a negative to a positive, right? So this sign change is what you need to understand whether the point is a local minimum or a local maximum. So let's stop the theory there and let's have a look at an example so that it's easier. So then you see the full um, problem being solved, optimization problem. So here we have an example, worked economic example. So I'm looking at this. So you're given a function, your utility function u of xy equals to root xy. And you're told your constraint function, this is subject to 4x plus 2y equals to 40, where both x and y are positive. So what's the first thing we need to do? Step number one would be to set up the Lagrangian xy lambda, your objective function, plus lambda times your constraint function minus 2y. Then your second step is to set up the first order conditions. Da by L by da by x gives you y over, what do we get here? When we differentiate this, we would get y over x. Make sure that you get the differentiation correct, because that's one place you can go wrong. Um, Minus 4 lambda equals to 0. So that is y over x square root of that equals 4 lambda. That's your first equation. And then I partially differentiate your Lagrangian with respect to y. And then I would get half x over y square root of that minus I get 2 lambda and I set it to 0. So from that I get half x over y square root of that equals to 2 lambda. That's my second equation. And the third equation is Lagrangian with respect to lambda. From that I get simply the constraint 40 minus 4x minus 2y equals to 0. That's my third equation. Now from the first and second equation, if I simply divide the first by second equation, I get y over x equals to uh, y over x equals to 2, from which I get y equals to 2x. And by substituting my fourth equation in my third equation, I get 40 minus 4x minus 2 times y is 2x equals to 0. So from this equation, I get x star, the value of x star as 5. And since x star is 5 and y is equals to 2x, y star is equal to 10. Since I know my x and y now, I go and substitute these values, let's say in equation 2 to figure out lambda. So equation 2 is half x over y square root of that equals to 2 times lambda. So from this, I would get lambda star as 0.177. Okay, so we figured out x, y, and lambda. That's fine. Now we need to figure out whether this x, y, and lambda gives me um, the maximum for utility or a minimum point for utility. Ideally, I would want to maximize utility, and that's what I've been told here, maximize. Right, so I need to figure out with this whether x equals 5 and y equals 10 actually maximizes my utility function. So now this is where I need to write down my bordered Hessian matrix 0, gx, gy, Lagrangian LXX, Lagrangian XY, Lagrangian YX, Lagrangian YY. Okay, so I have how many components here? 4, 5, 6, 7, 8 components that I need to figure out. Okay, let's first partially differentiate um, your constraint function. What is my constraint function? 4x plus 2y. My constraint function, let me write it down. 4x plus 2y equals 40. That's my constraint function. So if I were to partially differentiate my constraint function, which is g of x, equals to uh 4. Let me see here. Sorry, I had to write this down. So my constraint function g of xy is 40 minus um, 4x plus 2y. 40 my implicitly, I have to write it down implicitly. So dabba g by dabba x is simply gx, which is equals to minus 4, because this is how I wrote down my constraint function in my Lagrangian originally. So I need to write it down like this. Then that's one component done. That's this component, g of x, g of x. Then my next component, I'm going to calculate dabba g by dabba y. So that is gy. That is minus 2. So that's this second component, gy. That's also done. Now I have to partially differentiate my Lagrangians. Right. So Lagrangian, I've already partially differentiated it once with respect to x. That's what you got here in your first equation. And once with respect to y, that's what I got in my second equation. So this here is Lx, this here is Ly. What I simply need to do now is compute the second order derivative for my Lagrangian with respect to x, and compute the second order derivative of my Lagrangian with respect to y, and compute the partial derivative of the Lagrangian with respect to x and y. That's what I have as these components in my bordered Hessian. So how do I go about doing that? So L of x was what? What was L of x? Half square root of yx, um, and minus 4 lambda. Minus 4 lambda. So if I were to partially differentiate this again with respect to x, I would get, um, this is where you need to get it correct, y over x cube square root, and this part over here, minus 4 lambda is 0. So that's also done. And if I were to take partially differentiate this original function with respect to y, I would get 1 over 4, 1 over square root xy. Right. There's one other component. So what is my partial derivative of the Lagrangian with respect to y? It's this over here, this one. So half x over y, half square root of x over y minus, what was it? Minus 2 lambda, minus 2 lambda. So I partially differentiate this again with respect to y, and I would get um, minus 1 over 4 x over y cube. This also should be minus. Right. So now I figured out all the components in my bordered Hessian. Why is that? Because I've computed um, L of xx. That's what I need to insert here. I've computed L of xy. That's what I insert over here. And since I said L of xy equals to L of yx, this is also known. And I've computed L of yy. So I have all components. Now I simply go and put in all these components in my bordered Hessian matrix. So 0, what is gx? Gx is minus 4. What is gy? Minus 2. Gx is minus 4, gy is minus 2. Lxx is minus 1 over 4, y over x cube, square root of that. Lxy is 1 over 4, 1 over xy. And the same thing for Lyx, 1 over 4, 1 over square root of xy. Lyy is minus 1 over 4 x over y cube. Now, I know the values for um, my x and y. So what was x? X was 5 and y was 10. X was 5 and y was 10. So if I were to substitute in these values x and y to this bordered Hessian, you would get, I simply copy paste these two. The components you would get would be root 2 over 20. This is minus 1 over 20 times root 2. Then component over here would be 1 over 20 times root 2 and minus 1 over 40 times root 2. And now you check the signs. What are the signs? So you first take this component over here and you name it as, let's say, your Hessian matrix, 0 minus 4 minus 4 minus root 2 over 20. And you calculate the determinant of this. So the determinant of h, if you remember, how you calculate this multiplied by this minus 4 times minus 4, you would get minus 16, and that is less than 0. Then you take the determinant of the whole thing, determinant of B, which is a 3 by 3 matrix. So the determinant of B, when you calculate, you would get 1.131, which is a positive number. Now you have to remember how you calculate the determinants here. So now you see, you get the determinant of H, which is negative, and the determinant of B, which is positive. Therefore, you say that the points x star, which is 5, y star, which is 10, gives you a local maximum. That's what you get. So I know this is quite a long procedure because there's a lot for you to do here when you're considering the bordered Hessian matrix and figuring out whether the points are a local maximum or local minimum. So you need to be very fast at calculating this. So I've given the answer here in this particular example, the solution. So go through it again. Remind yourself how to calculate the determinants for 2 by 2 and 3 by 3 matrices. That's why we did that first before coming into this lesson. Um, so that's an example of um using the Lagrangian in a constraint optimization case. Right. Now, I told you before, we were talking about problems with equality constraints. We were talking about problems with equality constraints. You see here, these are equality. Now, what would happen if we didn't have an equality constraint? Now we are trying to relax some of our assumptions. If we didn't have an equality constraint, then we would have this inequality constraint. And with that, we get an additional set of conditions called these Kuhn-Tucker conditions. Now, this section, I will not, this will not come in the exam, so you don't have to go through it and you don't have to worry, and I will not go through it now also. This will not come in the exam. Please take note of that. But what's important is that you know that such a thing exists. So if in the case of you having an inequality like this, um, what do? You don't simply use the Lagrangian. There's another additional set of conditions that you have to consider. And that set of additional conditions is called the Kuhn-Tucker conditions. So I've given a basic introduction, and these are those conditions that you have to check. So for someone who's doing their further studies, maybe you can read through this and get an understanding. In the case of a inequality constraint, what do you do? And it's good to know that such thing exists. And I given a practice problem here as well. So, and a bit of a visualization of what's happening. But that section will not be tested in the exam. Just go through it for your knowledge. Then I come to this Lagrangian multiplier, some applications where, like I said before, if we've been looking at utility maximization, which is a consumer problem where you have trying to maximize utility subject to your, let's say, budget constraint. And then another application is a firm is trying to minimize their costs. So that's a firm problem where they're trying to minimize costs subject to given inputs in terms of labor and capital. And then you can have another type of problem, which is a firm is trying to maximize profit, right? And that's another type of example. So these are some economic applications, what I've talked about for constraint optimization. And I want you to take a little. So I've given some practice problems here for unconstrained problems. We don't need to go through those. But what I want you to do is um, take 10 minutes and look at this constraint optimization problem. Before going to the solution, try and do it by yourself. Take 10 minutes, try and do this by yourself, and we'll do this. And I'll also do it afterwards. And you see that you need to get some practice going into these questions so that you can do it faster. So just take 10 minutes and try it yourself. So how do we go about doing this particular problem? So in this particular problem, you're asked to maximize this particular utility function u of x1 comma x2, um, u of x1 comma x2, which is given by x1 to the power 0.3, x2 to the power zero point 0.7 subject to this particular uh, function. So your budget constraint, you would write it down as 2x1 plus x2 equals to 60. So what's the first thing you do? You would write down your Lagrangian x, y, lambda equals to your objective function x1 to the power zero point 0.3, x2 to the power zero point 0.7 plus lambda times 60 minus 2x1 minus x2. And then you write down your first order conditions. So you're partially differentiating your Lagrangian with respect to x. So here I would get zero point 0.3 times x1 to the power minus zero point 0.7 times x2 to the power zero point 0.7 minus 2 lambda equals, and I set it equals to 0. That's my first equation. Then I partially differentiate my Lagrangian with respect to y. So I get zero point 0.7 x1 to the power zero point 0.3 x2 to the power minus zero point 0.3 minus lambda equals to 0. That's my second equation. And my third equation is I partially differentiate my Lagrangian with respect to lambda, where I get the constraint function minus 2x1 minus x2. I set it equal to 0. Those are my three first order conditions. And from those three first order conditions, if I take 1 and 2, and if I divide 1 by 2, I divide 1 by 2, um, I should get, so what do I get? 0.3 x1 to the power minus 0.7 x2 to the power plus zero point 0.7 divided by zero point 0.7 x1 to the power zero point 0.3 x2 to the power minus zero point 0.3 equals to lambda cancels off equals to 2. 2 lambda divided by lambda. So lambda cancels off because lambda is not equals to 0. And from this I get 3 over 7. And if I rearrange the terms, I get x2 over x1 equals to 2. So that means I get x2 is 14 over 3 x1. I go and this is my fourth one. So I substitute equation 4 in 3 such that I get 60 minus 2x1 minus x2 is 14x1 over 3 equals to 0. And from this, I get x1 would be 9. That's 1. And then x2, I would get as 42. And if I go and substitute x1 and x2 in my, let's say, first equation, I would get lambda as something roughly 0.441, right? So that's the answer you get, and that's what I've given here as the solution. Just check. Sometimes there might be incorrect. It could be some of these solutions could be incorrect, but what matters most is the method in which you get it. So these are the first order conditions that I wrote down over here. These three equations. That's what I've given here. And then what I've simply done here and here is solving these first order conditions. That's what I've done in this area over here. Right. That's one example. Let's look at one more and then we can conclude the lecture. Let's see with the second order conditions. Yeah, let's look at this particular problem. So I've given the solution, but let's have a look at the problem. So we are looking at a constraint problem, and we are introducing the bordered Hessian test to check whether the x and y values actually give us the maximum value for this particular function. So we are asked to maximize the function f of xy, which is equals to 4x plus 3y. We have to maximize x and y such we have to get x and y such that it maximizes the function xy, subject to my constraint g of xy equals x squared plus y squared equals to 1. Right, so let's set up the Lagrangian. There's only one constraint, and lxy lambda equals to 4x plus 3y plus lambda times 1 minus x squared minus y squared. That's my Lagrangian. Then I write down the first order conditions. What are the first order conditions in this particular case? So I would partially differentiate my Lagrangian with respect to x. So I get 4 minus 2x lambda. 4 minus 2x lambda equals to 0. That's my first order condition. Then the Lagrangian I partially differentiate with respect to y. And in this case, I would get 3 minus 2y lambda equals to 0. And finally, I partially differentiate with respect to lambda, where I simply get the constraint and I set it equals to 0. So from this, if I divide 1 by 2, I get 4 divided by 3 equals to 2x lambda divided by 2y lambda. And lambda cancels off, 2 cancels off, lambda, since lambda is not equals to 0. So I get x is 4 over 3 times y. And by substituting the fourth equation in the third equation, I get 1 minus x squared is 4y over 3 squared minus y squared equals to 0. And from this, I would get y to be, so this is interesting. So here, since it's y squared, you would get two values. So you would ideally get for y, I think, let's just check, um, solve this to see. 1 minus 16y squared over 9 minus y squared equals to 0. 1 equals to 16 plus 9 is 25 over 9y squared. So y is 9 over 25, square root of that, which is plus uh, square root of that, plus or minus. So plus or minus 3 over 5. So that is y is equals to plus or minus 0.6. So y can be, what this means is y can be either plus 0.6 or y can be minus 0.6. So if y is plus 0.6, x x would be plus 0.8, or x would be, if y is minus 0.6, x would be minus 0.8. And for these values, x and y, if x is plus 0.8, y is plus zero point 0.6, you get lambda as plus 2.5. Or if y is minus zero point 0.6, x is minus zero point 0.8, you would get lambda as um, minus 2.5. Now you have several values here. So you have either zero point 0.8, 0.6, 2.5, this value, or minus zero point 0.6, minus zero point 0.8, and minus 2.5. Now you need to figure out which combination of values. So there are two combinations. Your first combination is this is your second combination. Which combination of values gives me the maximum value for your function f of xy? Right? That's what we had to do, because we are asked to find, if you look at the left hand side, we are asked to find the maximum for your function, right? So this is where now we use the bordered Hessian matrix. So we have to use the bordered Hessian matrix, which is given by this equation, this matrix. Lagrangian xx, Lagrangian xy, Lagrangian yx, Lagrangian yy. I always write it down, the matrix. Now, if I were to calculate, so g is g of xy is 1 minus x squared minus y squared. I have to write it exactly in the form I've written in my Lagrangian, in this form. So then g of x is minus 2x and g of y is minus 2y. And then for my Lagrangian, L of x, I have already calculated. What was L of x? L of x is 4 minus 2x lambda. 4 minus 2x lambda. What was L of y? I think it was 3 minus 2y lambda. 3 minus 2y lambda. So from this, I can calculate Lxx, which is minus 2 lambda. Lyy is minus, again, 2 lambda, and Lxy, which is also equal to Lyx, is equal to 0. So I substitute, so for my B, 0, what is gx minus 2x? Gy is minus 2y minus 2x minus 2y. Lxx is minus 2 lambda. Lxy is 0. Lyx is also 0. Lyy is minus 2 lambda. So now I have two candidates of values for x, y, and lambda. So if the first candidate is x, y, lambda, where it's equal to the plus values, plus 0.8, plus 0.6, and plus 2.5. This is my first candidate. So if for my first candidate, what is my bordered Hessian going to be like? 0, minus 1.6, so 2 minus 2x, x is 0.8, minus 1.2, minus 1.6, minus 5, 0, minus 1.2, 0, minus 5. So here I calculate first the Hessian part, which is this top part over here. I take this 0, minus 1.6, minus 1.6, minus 5, and I calculate the determinant of this. So the determinant I would get when you calculate as minus 2.56, which is less than 0. And then I have to calculate the determinant of my 3 by 3 matrix B. So you get, when you calculate it, plus 20, which is greater than 0. So here you would get, for this particular candidate, what is the candidate? 0.8 for x, 0.6 for y, and 2.5 for lambda. For this candidate, you get a, because of the sign difference from negative to positive, you get a local maximum. This point gives you a local maximum for your function f. But if you consider the candidate x, y, lambda, the negative values, minus 0.8, minus 0.6, and minus 2.5, if you go through that whole process of calculating your bordered Hessian, and then from that you calculate your determinant of B, you take your Hessian and you calculate your determinant of H, what you would get is, for the determinant of H, you would get a negative value. And for the determinant of B also, you would get a negative value. You will see that when you calculate it. And from that, you don't see the sign does not alternate. And because of that, we say that the bordered Hessian um, test actually fails in this occasion. So this second candidate is not the answer that we are looking for. The answer that we are looking for is this candidate, the first candidate, where all numbers are positive, and from that you get that these values gives you a local maximum. So that's what I have given in this particular solution. So it's a very long answer that you have to consider. And because of that, so I say the constraint maximizer is x star 0.8, y star 0.6 is the answer that we are looking for. Because we are looking for the answer that maximizes the function f of xy. So we did a lot of things under this constraint optimization. I did a few updates to this particular lecture, and I would advise to all of you, since I have it in this Google Drive, rather than downloading it for now, keep it in the Google Drive folder and open it in the Google Drive folder itself, because then if there are any updates to the lecture, you will have it in the Google Drive rather than in your local file. So just a piece of advice from my end. If you have any questions, please do ask. I know it's a very long and tedious lecture. Um, for this, you need to sit down and you need to do your own calculations. So follow these steps. It's very mechanical, the steps. Go through those steps. If you have any questions, do ask. Send me an email or a message. So we will wrap up for today. Thank you very much.
Thank you, sir. Thank you very much, sir.